Hello, everyone, and welcome to the new semester of the ITC Colloquium. Today, we will be hearing from Dr. Nico Garavito Camargo. He is an Einstein Fellow at the University of Maryland, studying dynamics of the Milky Way and its satellite galaxies. He received his PhD from the University of Arizona, and this summer, he will be starting as an assistant professor at Universidad Católica de Chile. So, everyone, welcome, Nico.
Morning, everyone. It's a pleasure to be here, maybe the coldest colloquium of the semester. So it's really special to be here at the CFA with a lot of the foundational work in this field have been done in this place. So I'm very excited to tell you about what has been done in collaboration also with some of the groups here. So I'm going to talk about mapping the dark matter distribution in the Milky Way halo and what can we learn from that. So I'm going to start with this beautiful image from the illustrious TNG collaboration, showing how a Milky Way-like galaxy, so in terms of similar mass as the Milky Way, formed since the beginning of the universe. So you see here the gas flowing through these filaments of dark matter. And then you see, okay, it started again. This is the stars forming from that gas cooling, forming the first stars, and then these stars enriching the medium, right? So it is very important to see that this gas comes from these filaments of dark matter. So dark matter plays a major role here in putting together all these galaxies due to the gravitational field that dark matter is having here. And this theory is being now really robust. In the last decade, we know a lot of hydrodynamics, how these galaxies form. So we really have robust predictions of how galaxies form and what is the role of dark matter in forming galaxies like the Milky Way. So of course, as you're gonna guess, I'm gonna tell you that the best galaxy or a good galaxy to study this is the Milky Way, because we have many observables. We have a multi-dimensional view of a galaxy as no other galaxy. And by that, I mean we have positions, we have velocities, and metallicities. So we have really not only 3D, 6D, but more than 6D dimensions to really start tracing all the processes that take place in the galaxy. So the goal is really to go from observations like this, from the Gaia satellite, to derive some properties of dark matter, okay? There are more things that could be done, and then in the field of near-field cosmology, there are these, to me, these are the big questions. So one, for example, is how lumpy are dark matter halos, right? You see a bunch of substructure here. These are like smaller subhalos. And it turns out that the amount of this, the number of subhalos that a galaxy like the Milky Way should have, it depends on the nature of dark matter in the model that you choose. The structure of these subhalos also depend on dark matter, like the density profiles of these subhalos also depend on that. So these are, if we can detect what is the population of subhalos around the galaxy, that would be a really nice test for dark matter that we still don't know what it is. But also we can test galaxy formation models, right? Like, the gas formed the first stars, and then those stars enrich the galaxy. So through studying this enrichment, how this process happens, we can learn a lot about the first stars, galactic chemical evolution, as Kelly has done amazing work in the field in this area. But also, then we can start tracing what is the distribution of dark matter in the galaxy, because we have a bunch of stars that we can observe, have millions of stars that trace this underlying dark matter halo. And that's what I'm going to focus on this talk. Okay, I'm at the way. Feel free to stop me at any point if you have questions along the way. So let's start a little bit with the basics. We have a very successful theory telling us how dark matter form in the universe, in the large-scale structure of the universe. So this is a very beautiful image of these dark matter filaments. And if we start zooming on where the halos form, like in the middle of these filaments, these bright spots, you start to see halos like this. So these are dark matter only. There are no stars here. And already you can see that halos have like different morphologies, right? So in general, we can characterize the shape of these halos using ellipsoids, which principal axis define what is the triaxiality of the halo. And I'm going to use this metric a lot, so I'm going to spend a little bit of time explaining this. So basically, if you parameterize these halos with this ellipsoid, then you can say, you can have quantities as this, like S value here, which is the ratio of the minor to major axis. And then if S is equal 1, you have a spherical halo. If S is less than 1, you have a triaxial halo. So we are very good astronomers at counting and doing statistics, so we can actually go back to this simulation and do a statistics of what is the shape of halos in these simulations. And this is what Chua did here. He was a PhD student here. And then this is in the illustrious simulation. You can see as a function of mass, of the total mass of the dark matter halos, what is the overall shape. So how much is flattened these halos or not. So remember, 1 is spherical, then lower values are more and more and more flattened halos. So a striking difference here, first of all, is when you look at illustrious dark matter halos without baryons, halos are really, really triaxial, very flattened. But once you put baryons, halos become more spherical, so larger values of S. That's because baryons fall into the potential well of the galaxy and they make the galaxy overall more spherical, right? The second thing that you see here, especially we focus on the red line, which is the galaxy with baryons, is that in the outer regions, so the dashed line, the halos are more triaxial, more elongated than in the inner parts. And that's because it has still more memory from the filaments where they're being accreted. Okay, so this is basics, kind of to build intuition on how halos shape look like. But then halos also evolve as a function of time. They are not static. They are being accreted a lot of material. And as they evolve, their shape can change. Not only their tilt, like the orientation of the major axis. This is a beautiful paper by Jesse Han, showing how the principal axis, the direction of the principal axis, can change as a function of time. So quite a bit, like for like 60 degrees or so in the last 6 gigayears. And in this case, this halo, okay, maintains the flattening, but sometimes it might change what is the axis ratios as a function of time, can stay constant or not. So how can these shapes remain constant? If the halo is embedded in a well-defined filament and the accretion is not very strong in the sense, not many major mergers, you'll have a halo whose principal axes are always aligned, and not only as a function of time, but as a function of radius. If you go outside in the halo, still your principal axis will be pointing to the right, to the same location. And here, by the way, I'm not plotting the principal axis, it's just the direction of the minor axis. That's why you see it perpendicular to the filament. And then in this case, this halo, for example, is embedded between many filaments, so the accretion is way more complicated, and then you can see that the shape, the vector of the principal axis showing with these blue arrows here are pointing everywhere, because basically at different radii, the halo shape has a different structure. So this is summarized in this kind of plot. So as a function of radius, what is the orientation of the principal axis? The yellow one is for this halo, M12W. This is from the fire simulation. So it just go in the inner parts have one orientation, but then it changes as a function of radius. While it's the opposite for this M12F halo that is in a very nice filament, it remains aligned as a function of radius. And the same for the shape. So this is, think about this as the S value that I told you before. So it's different in the inner regions than in the outer regions. Okay? So that happens in dark matter halos. But finally, also, these dark matter halos undergo mergers. And what happens during mergers? During mergers, depending on the mass of the satellite and the orbit, these mergers can sink very fast and change the shape of the halo, but also they leave this debris of stars everywhere. So you can start mapping how was that process. And something important is that if the merger happened earlier on, you will find remnants of the merger in the inner part of the galaxy, as if it is an earlier merger, or like a late merger, you will see still like tidal tails forming in the outer parts. So basically, where do you find the merger and the debris of the merger will give you information about when the merger happened. Okay, something else that happened in the host galaxy in particular is as the satellite orbits, it moves. So I'm plotting here the velocity of the center of this host halo as a function of time, and you see that at the first pericenter, this velocity this halo here, the host halo, feel like a rapid motion because it's reacting to the satellite that is infalling, right? This is what we expect for gravitational dynamics. So halos also, satellite galaxies impart a major perturbation, especially at the first pericenter passage. Okay, to summarize this, the introduction of halo shapes, now we have learned that halos in the inner regions are more spherical than in the outskirts due to the presence of baryons. In the outer regions, there is a strong triaxiality due to the filamentary structure. And then dark matter halo shapes can change as a function of time and radius, depending on the accretion process that they have been undergoing. And satellite galaxies really perturb the halos. So we can turn this again and then ask the question, okay, if we measure what is the halo response of a galaxy, can we back up the accretion process of the galaxy and the filamentary structure of the galaxy? And that's an important question to ask because it's very related to dark matter, right? Okay, but we don't observe dark matter halos, right? We can observe them, we observe galaxies, so this is, in this case, this is a dark matter halo from the fire simulation, and then you can see the stellar distribution in this galaxy. So the stellar halos are overall like very low mass compared to the total mass of the galaxy, roughly 1 to 5% of the mass of the galaxy. So very low mass, and it traces very well the gravitational potential of the galaxy, because mainly in these outer parts, that potential is governed by the dark matter halo. But the overall shape might not be traced by the stellar halo, we don't know. But then Jesse Hahn showing this very nice paper in the illusory simulation that the tilt of the dark matter halo is overall very well constrained by the tilt in the stellar halo. So this means that if we can measure any tilt here, any shape of this principal axis, maybe we can derive what is the underlying tilt in the dark matter halo. Okay. So of course, the best galaxy to measure this is the Milky Way, because part of the reason is because we have so many stars that we have measured, and then this is just some statistics from Gaia. So Gaia DR3 delivered 1.5 billion of stars with proper motions, so distances, proper motions. And later this year, Gaia is going to release the data release 4, which is going to be 2.8 billion of stars. It's a lot of stars in one galaxy, right? Just to give you an idea, how does it look like? Let's see if this works. Maybe I have to click here. Oh, sorry, I missed it. Let's see. So this is an animation from the Gaia collaboration, the consortium, and it's just showing how, if we have proper motions, we don't have just a picture, but we can have a video of the galaxy, right? So this is integrating forward the orbits of stars in the galaxy. So you see the motion. I mean, it's very high resolution, but yeah, you still can see how all of these stars are moving. If you assume a potential for the galaxy, you can see the movie of the Milky Way. So this is really the only galaxy we can do this, right? And if you have motions, you have orbits, then we can back up what is the underlying dark matter potential, right? That's the name of the game. Okay, maybe I need to click back here. Good. But Gaia is not the only one. It has been very important, but there are a lot of other spectroscopic surveys and also photometric surveys that have mapped the galaxy. So these are their footprints. And basically, you have a lot of a good velocity uncertainty, depending on the magnitude and brightness of the stars, right? But overall, we have a very good multidimensional view of the Milky Way galaxy. So what can we do with it? Why we need a multidimensional view of the galaxy? So this is a nice plot from an Roxanne Pop, actually showing that in this stellar halo of the Milky Way, right? You see, like, okay, something, it has a really massive stellar halo. Clearly, there has gone major mergers in the past, but how can we disentangle the mergers that happen here? So one way to do it is you plot this phase space diagram, which is basically velocity as a function of radius, and then you start to see these chevrons-like features, which are the remnants of satellite galaxies going around. Now, it still is very crowded, right? But then you have also metallicity, which is the color here, the color bar. So you start selecting by metallicity, then you can say, okay, let's take the metal-rich stars in this stellar halo. Then you start to clean up and say, okay, there is probably this accreted material from this satellite galaxy. And then if you select the metal poorer stars, then you get another kind of debris. So this is kind of the game. Of course, it's very easy to do in simulation because you know the absolute truth. But this is kind of the game. You have to play not only in configuration space, but also in phase space and also metallicities. And with that information, you start to extract where these stars are coming from in the galaxy. And I'm sure you have seen this very famous plot by Rohan Naidu when he was a grad student here, basically classifying all of the stars in the stellar halos up to 50 kiloparsec to which kind of merger where they belong, where they come from. So you can see that there are many small mergers that brought some fraction of stars, but really in the stellar halo there are two mergers that have brought most of the stars. And that's the Gaia, Sagittarius, Enceladus, and Sagittarius. So I'm going to talk a little bit about these two mergers to show what are the effects, how we detect them, and what are the effects on the dark matter halo, and what they're important to understand the dark matter halo structure. So the GSE merger, this is a nice movie by Gus Bain, showing how that merger happened. It was a head-on collision. More or less the mass of the progenitor of GSE was, roughly like 20% to 30% of the galaxy, so very massive. And this merger happened like something like 8 to 10 gigayears ago. It was discovered in some kind of metal-rich galaxies for halo standards, and then within eccentric orbits. And then the debris of these stars have been found all the way up to 100 kpc. So it brought a bunch of stars that mostly are in the inner parts, but still have some remnants out in the outer galaxy. Okay, so for our purposes, okay, what did it did to the distribution of stars in the galaxy? So when you look at the RL-RL distributions in the inner 40 kpc of the galaxies, so in this projection, this is the plane of the disk of the galaxy. You see that it's very elongated, right? And then when you see in the vertical direction, so the disk here you'll see like edge on, you see that there is some tilt of that RL-RL distribution of the stars with respect to the disk, something around 25 degrees or so. This is typically not found in a galaxy without major mergers. Usually this part is more spherical, so what could have caused that? It turns out that this is what Jesse Hahn did too, but others have done recently, is like you need to have a dark matter halo that is kind of backing up or like supporting this structure. And this is, dark matter halo is consistent when you run this simulation with the GSE merger. It's the remnant, the response of the galaxy to the GSE early on still kind of have a tilted dark matter halo that sustains this kind of distribution. So this is the kind of things that we can do now. We observe the distribution of stars, and then we can see, okay, what kind of potential do we need to sustain this structure that we see, okay? So basically, the inner parts still of the halo are governed by the remnants of this merger that happened some 8 gigayears ago. Now, the second merger that is going on right now is Sagittarius. Sagittarius is a galaxy that is lower mass compared to GSE and probably fell into the galaxy for the first time like something 8 gigayears ago. And it's been orbiting since then. So once the galaxy finished merging with GSE, then Sagittarius came. But Sagittarius is a lower mass galaxy, so maybe 1/20th of the galaxy in mass. And then you can see here in RL-RS, these are the tidal streams from the GSE that you can see, from Sagittarius. So you see these very nice tidal tails here wrapping all around the galaxy. So this is the edge of the galaxy, this is the sun, and right now the progenitor of Sag is somewhere in the southern hemisphere of the galaxy around here. This is very useful to have these tidal tails because these tails basically give information about the underlying potential of the galaxy, right? In order to model, when you model this interaction, you need to assume a gravitational potential to reproduce these streams, and then people have done this. And then this is work by Eugene Vasiliev, and basically this has been actually a challenge to do for many, many years. Even though this galaxy was discovered in the 90s, early in the 90s, it's been really challenging to really reproduce this kind of morphology. But recently, Eugene Vasiliev, including more modern models for the galaxy, has come up with something like this, which is, okay, in the inner part there is some proletness for the halo, some elongation, but it changes drastically as you go farther out in the halo. So we are starting to see that the distribution of dark matter in the galaxy is not the same as a function of radius, it's different, most likely because of these mergers are happening. Okay? So this is not the final truth, but it's just to illustrate how, by mapping these stellar streams, we can start to uncover what is the underlying distribution in the galaxy. Okay, but finally I want to talk about my favorite merger. So I want to come back to this very nice figure by Gaia, and that's the merger with the Large Magellanic Cloud and the Small Magellanic Cloud. So the LMC currently is at 50 kiloparsec. It just passed its first pericentric passage. And we think that more or less the mass of the LMC is 1/10 to 1/5 of the mass of the galaxy, so very massive galaxy. The orbital histories were derived actually here by Gurtina, Beslan, Iteka, Yuvalali, when they were grad students here, just showing how this galaxy came from first info into the galaxy. So you put it side by side. This is the Milky Way, an illustration of the disk of the Milky Way. This is the LMC, and then as seen by Gaia. So it's pretty big, and actually this dashed line is showing where we have found more stars of the LMC with deeper imaging than Gaia. So it's a pretty big galaxy, right, when you put it side by side. When you see it in the Gaia projection, you see it like a small galaxy, but when you put it side by side, you really see the size of the galaxy. So if the LMC is coming for the first time, you expect to be hitting the Milky Way halo and perturbing the halo substantially. So what I'm showing here is a simulation that I did some time ago now, just illustrating how, as the LMC comes, is moving the dark matter halo of the Milky Way and the entire galaxy. And one important thing is like, look at this inner part of the galaxy gets accelerated a lot at the end by the pull from the LMC. This is known as the reflex motion. This was a prediction at the time, like the whole galaxy is not in equilibrium, like the inner parts are moving faster than the outer parts. You can see it better in this image where you're like in an inertial frame, and then you plot what are the velocities across the galaxy, and then you see that the inner parts of the galaxy are moving faster than the outer parts, and in a different direction, not only faster, but toward a different direction than the outer parts of the galaxy, during this interaction. And this is a very nice image by Eugene Vasiliev, which wrote a very nice review about the LMC interaction with the Milky Way. And then we have predictions of how much was this effect, right? So at what distance you will see larger this effect, because of course we are in the galaxy, we are moving in the galaxy, so we shouldn't see the effect here because all of this is moving with us. But the outer regions, we should see a differential motion when you measure the velocities of the stars, okay? So we did these predictions, and this is a nice plot by Vedant from last year showing the direction of this motion. When he measured the velocities in the outer halo, like beyond 50 kiloparsecs, then he saw that there was a net motion in the galaxy, actually. Like, if the galaxy would be in equilibrium, we shouldn't see any net motion in the outer halo, but we do see a net motion. And then these contours represent different probabilities of where that motion is happening, and it's happening to our previous position in the orbit of the LMC, as expected from the interaction with the LMC. And then in this plot here, you see as a function of radius, what is the magnitude of that velocity, the relative motion between the inner and outer halo, which is called V travel. And then you see that it can go all the way to 60 kilometers per second. So this is proof that this merger is actually perturbing the galaxy a lot. Okay, the second thing that happens when you have a merger happening, going on, is that, so in this plot here, I'm showing you the density of dark matter in the Milky Way halo, so no LMC particles, and what you see here in dark blue is a dark matter wave being induced by the satellite. So the satellite orbits, it gravitational pull a bunch of dark matter particles in the Milky Way halo that then pile up behind the satellite and then create a large overdensity of dark matter behind the satellite. This is what created dynamical friction, described by Chandrasekhar in the 40s, and what made the satellite decay. So this should exist in any dark matter model. We should see a dark matter wake. And then the present day distribution, this is the whole evolution of the Milky Way, and these are the prediction of the density contours of overdensities in the halo are in dark blue, showing that if the galaxy is here, this is the orbit of the LMC, you should see this dark matter wave here. And then this big collective response, which is due to the motion of the galaxy relative to the outer regions, you should see a large dipole in the opposite side of the galaxy. And then this is something that Charlie did here, basically looking at K giants in the outer halo. This is thanks to Gaia and WISE. And then you can, yeah, question, sorry.
All of these predictions
Yes.
depend on the size of mass of the halo, right?
Yes.
How well is that known?
Okay, great question. Because I think right at this point we were like, okay, if the LMC is massive, we should see these perturbations. So the game here was like to try to find those perturbations. Now we find them. Now we're like, okay, what can we constrain exactly? So we are at that. I feel we have done a lot of progress. I'm going to talk more about that later. But I would say, like, for the LMC mass, for example, I think we're in a factor of 5 now, right? What is the mass? Before, maybe it was like 10. Same for the Milky Way. The Milky Way, now we are starting to constrain more and more the properties. So at the end of the talk, I'm going to mention more, but the goal to me right now is what can we do from these observations to back up properties of those mergers, and maybe from dark matter? Yes, Katie.
I have one question from the prior slide as well. I was curious about the scale. So, like, looking
Yeah.
at this image here, it looks like a huge response.
Yeah.
Is it as big as it looks?
It is big. I mean, we don't know yet. Like, okay, yeah, this is the disk of the galaxy. This is, I should put a scale here. This is like 300 kpc. So it's a pretty big expectation, but we haven't observed in the outer parts yet. But I'm going to come back to that. Because basically this is predicting that most of the perturbations are in the outer part of the galaxy, which we are starting to look with Gaia. We're starting to observe them. Okay, so this is what Charlie showed with K giants, and basically showing that there are like two large overdensities, one that is very coincident with the wake, right? And one with this northern dipole due to the motion of the halo. There is a lot of debate still because there is substructure that we don't know, so really the amplitude of how this is still in debate, but it's clear right now that there is this overdensity that, especially the one here, that it doesn't seem to be substructure. A stellar stream in the outer halo cannot create such overdensity. So we're still figuring out what is going on, but it's very exciting to see this. Further proof from the wake has from Manuel, which was a PhD student in Chile, and now he's at Leiden. And with DECAM, he went really, really deep in 4 fields across the wake. Oops, I think, okay. These 4 fields across the wake, so in some, the idea was to find what is the edge of this wake and what is the radial extent of the wake. So in these 4 tiles, he looked for the stars, for main sequence of stars and red giants up to 90 kiloparsecs, and then as a function of right ascension here, can plot what is the total density of stars here. So you see that in the tiles that are in the edge, you don't see any upper density, but when you go into the wake, you start to see a big increase in upper density, which is consistent with simulations, right? And it's really hard to reproduce with stellar halo substructure. These are this red band here. When you put a lot of substructure in the outer halo, it's really hard to produce an upper density like this. So we're starting to prove, again, the extent, the morphology of the wake, with the goal in the future to start to constrain properties of the merger. So that's where we are right now. So for the dark matter halo shape that we were talking about, what such a merger like the LMC will mean, we already talked about the wake and the reflex motion. And one challenge that posing for modelers is that you can see that the distribution here of dark matter is loop-sided, right? Because you have this response because the LMC is right at pericenter, so it's moving the galaxy. So this loop-sided distribution that is really hard to capture with ellipsoidals, with triaxial shapes, as we do for large cosmological halos. So we need to think about different metrics because these ellipsoidals always assume axisymmetric distributions, which is not the case. And then some consequences of this is that the underlying potential of the galaxy is not static and is not spherically symmetric, it's not axisymmetric. So it put a difficulty, but also an opportunity to derive the orbital properties of any halo tracer in the other parts of the galaxy. So this is an example of an orbit integrated in a potential that it doesn't fill the LMC, that's the white line, but in the red line or the orange line, you can see what happened when you include the perturbation from the LMC. So you really have two different orbital histories. So it's really hard to disentangle what is the orbital histories of halo tracers if you don't take into account the LMC. But then you can reverse the problem. You can say, like in the Sagittarius case, what have to be the properties of this merger in order to reproduce the observations of the Sagittarius stream, right? Okay. So to summarize the LMC part, the consequences of this merger, you will see this in overdensity of stars. We see this in the velocity made by Vedant and others. And what can we get from this? So I think it's a unique opportunity to understand how halos respond to mergers, because we are living right now in a time that we are merging with a massive galaxy, so we can measure that as in any other galaxy. And it has consequences that are, I think, very exciting, and I want to highlight a couple here. One, for example, is this paper by Jesse Hahn and Scott here too, where they look at a population of hypervelocity stars with unknown origin, and when they include the effects of the Large Magellanic Cloud, so coming back to these orbits, when they include these potential effects, they found that 9 hypervelocity stars with unknown origin came from the black hole from the center of the LMC, and we didn't know that before, so that's pretty exciting. Similarly, satellites that were in the Milky Way that we didn't know what their origins were associated with the LMC. So the LMC that doesn't only come with the SMC, but with 6 other satellite galaxies. So we are looking at a group info, and then we are starting to prove the origin of satellites, which is a prediction from the CDM, right? So different dark matter models will predict different numbers of satellites from these dwarf galaxies. So this is pretty exciting in general for understanding dark matter and galaxy formation. Scott Lucchini has done also amazing work studying the CGM, the gas that is also being ramp pressure stripped from the SMC and the LMC as they interact into the Milky Way. But I'm not going to talk about it. I'm sure you have heard a lot from Scott. But for me, it's also very important to study what is the response of the dark matter halo shape to the LMC. Okay, so to summarize the timeline of major accretion events in the Milky Way, we have here look-back time, so the present time is here. We have the GSE merger that happened a long time ago, sometime between 10 and 8 gigayears. Then Sagittarius, which is still going, is a lower mass merger, that's why it has been lasting for long. And then the LMC and the SMC are coming. And then this is the radius, or where we found most of the stars. So GSE is in the inner part, Sagittarius is more intermediate, and then the LMC and the SMC is perturbing more the outer halo. So with the GSE, we learned more about the inner halo shape. I showed you that plot from Jesse Hahn, how the inner halo is being disrupted. We also learned about chemical evolution of galaxies, which I haven't talked about in this presentation so far. And then with the Sagittarius, we have seen perturbation from Sagittarius in the disk, which I haven't shown, but it has been really important. And then we can map the halo shape in these intermediate scales with the stellar stream from Sagittarius. And then from the LMC and the SMC, we are measuring an early stage kind of massive merger and the response of the halo to the LMC. Okay, so what's next, which is the question that I got. We have a bunch of new telescopes and observatories coming, right? We have the Vera Rubin, Gaia DR4, SDSS-V, Formos, VIA, which is actually being here led by Charlie, and then PFS with a bunch of spectroscopic surveys. So this is amazing because we're going to deliver even more data. And then this is an image from Robin Sanderson showing where that data is what is going to allow us to see. So for example, if we focus on, let's say, BHB stars here, we'll be able to map really all the outer parts of the galaxy. This is almost like 1 megaparsec away from the center of the galaxy. We're going to see all of the BHB stars in this region. So really the outskirts of the galaxy, beyond the outskirts of the galaxy. And then it depends on the tracer that you use. You can go more further. This is with astrometric measurements. With the spectroscopic, you're going to go a little bit like in the inner parts, but it's still all the way to 300 kiloparsec. So where we predicted the wake to be, and all of these effects from the LMC to be more important, and also from the filaments, right? Filamentary structure, we're going to start to probe these regions. Okay, I'm doing on time, good. But to really maximize this, you see that it's really hard to, we need a lot of models. So what do we need to maximize the output, scientific output from these observatories? And one is more simulations. Really, we need more predictions. In particular, I'm excited to think about what are the predictions from these perturbations from these satellites will depend, or will look like in different dark matter models. If you have, for example, self-interacting dark matter model, warm dark matter models, is there any differences in the perturbations that these galaxies has, these satellite galaxies imprint in the halo of the Milky Way? Same for the filaments. And also in methods. We need methods to really learn to quantify this. I showed that we have this triaxial method, this ellipsoid, but this start to be complicated when you have so much detail. We need better methods also to compare between simulation, between models. We need a standard metric that allow us to compare these halo responses in the simulations. And then how to model, how to connect, for example, simulation with observations. All of these will have different selection functions, which are hard to model, and then we need to take into account when we are comparing, because we are entering that data of making more precise measurements of the galaxy response with these surveys, but we need these methods. Okay, so I'm gonna focus in these two things for the rest of the talk. How can we systematically compare the halo response across simulations? And then what is the magnitude of these merger-driven effects in the Milky Way halo once we have these methods? So one of the methods that the main method I'll be talking about is this called basis function expansions, which is basically you have a simulation, you have your particle data, and then you can decompose all of this density field in a basis, right? You can always do that. And then you can impose in the basis now that you satisfy the Poisson equation. So this basis, I'm not gonna go through the math, but I'm just telling you that this basis satisfies Poisson equation. So it's really good for self-gravitating systems like dark matter halos. And then this is a reconstruction of this particle distribution using the basis. And now the beauty is that you can decompose this basis, think about the spherical harmonics. So you can say like, okay, how does the dipole look like in this response? And then you see the dipole. How does the quadrupole look like? How does high order modes look like? So now you have a framework that is allow you to really start to decompose the response of a halo in terms of these spherical harmonics or this basis. And a nice thing also is that these connect with perturbation theory of self-gravitating systems, and this is a lot of work done by Martin Weinberg for the last 30 years or so. So there is a nice correspondence there. So I'm just going to show you how a merger like the one with the LMC will look like in this space. So this is this is the harmonic order. So L equal 1 is a dipole, L equal 2 is a quadrupole, and so on. And this is the order of how strong is the response in this space. So now we are going from analyzing and seeing these nice movies. Now we go to see this kind of plot here. And then you can see, okay, this is already happening. Okay, this is where we start. At the beginning is only a monopole, a spherical halo. And then as the LMC start to come, you start to build up a lot of power in all of these high order terms. And then focus on this. This is the dipole, right? After the pericenter passage, the dipole will get very excited. That's why, because you are moving the galaxy. So you induce this collective response, this density, this dipolar response, you will see it right after pericenter. So really now we have time series analysis of the halo response, and then we can do a lot more. So this is when you plot this now as a function of time. I'm showing here, for example, this is the dipole, the L equal 1, and then you see how it peaks right after pericenter, that is shown by this dotted line here. You see how the dipole get excited and then decreases and then get excited again in the second pericenter passage and so on. So now we start to understand galactic dynamics and halo dynamics using this space. I just want to note here that the dipole is the only one that gets excited after pericenter passages, and all of these get excited before. That's because these ones have information about the dark matter wake. That matter wake is not easily captured by one harmonic order here, but just it's a combination of many. This is why you see all of this increasing in time. That's like that wake getting formed. Okay, I'm not going to go into much detail, but this is fun to see, and this is a nice framework to understand halo decomposition. So we have done that in idealized simulations, but what about cosmological halos? Here we have ignored a lot of effects, like filaments, a lot of substructure is going around the galaxies. So it's really the halo response as simple as we have done it in idealized simulations. So this is something that Elise Darraford did when she was a grad student at Stanford. So this paper is in press in APJ, and basically looking at cosmological simulations that have LMC analogs. These are called the Milky Way EST simulations, embedded in a cosmological setting, and then we found these 18 analogs that have similar properties to what we think the LMC merger has done. So coming back to understanding what are the different responses of the halo when you have variations in the orbit, in the masses. And then, so I'm going to do a small quiz here, but I already showed you that this is the halo response for the Milky Way in isolation. So now I'm going to show you two responses of these cosmological halos. One is without an LMC mergers, and one is with an LMC merger. And then I just want to ask you, what do you think this merger is? Is this one with the LMC or without the LMC? So if you think this is with the LMC, raise your hand. Okay, and do you think this is with the LMC? Wow, yes, you're paying attention. Right, and the key here is the L=1, right, the dipole. There is no dipole here. This was a major thing that we were wondering, like, it's easy to excite a dipole in a cosmological halo where there are so many things happening. Okay, and the answer is no. So Elise looked at all of these halos, and for all of these halos, so we align them so the merger is at t=0 here in this axis. And all of these dipoles get excited after the merger, except this halo, because have a previous merger before. So of course you have a dipole. But it's just showing that how the dipoles are very unique to this halo response. And then this is color-coded by the merger mass ratio. So again, coming back to that question, like the higher, the larger the mass ratio, the larger is the dipole here, right? So if there is a minor merger, so you see a tiny dipole, and if you see like a large merger, you will see a large dipole. I think also there is information about when the peak happens. It has to be related with, in my opinion, to what is the dramatic halo particle, the nature of the particles. If you have self-interactions, you will damp this, you will delay this response, but we have improved it. But it's just to show you what is the kind of thing that we're thinking about. So this is in the halos that have LMC-like mergers. Yeah. So when we compare this to the evolution of the halos without massive satellites, so this is the amplitude of the dipole. You see no dipoles at all. Like, it's really hard to excite dipoles. Here we have filaments of their substructure, but we will never see a dipole. So this is starting to say that dipole is a clear signature of a merger, and a merger that is just after pericenter, right? If you see it after here, like 2 gigayears after the pericenter, you wouldn't see much of a dipole. Okay, so this is a very nice prediction. And then let's say that we measure this dipole, let's say from the kind of maps that Charlie has done, in the outer halo, we measure the dipole. What can we get from this, the amplitude of the dipole? So we can back up the mass of the merger. There is a nice relationship. There is something interesting here that also we found is that these halos that are in cosmological simulations have like a different kind of a scaling relationship with the mass ratio than the halos that are in isolation. The ones that are not in a cosmological halo, like the idealized simulations, have a different response. And we quite don't understand why this is happening, but that's something interesting that we are looking into it. But it's nice to see this relationship. There is also this relationship from the amplitude of the dipole versus the displacement of the inner halo versus the outer halo. We don't know how much is that displacement. We have prediction, but we haven't measured it. It's really hard to measure how offset is the outer regions of the galaxy with respect to the inner regions. So this is a nice prediction that depending on the amplitude of the dipole, it will give you an information of how much is that displacement. So this is the kind of things that we're starting to think about. And again, yeah.
Is there also an effect from rotation of the halo?
Yeah,
Does that have some influence on the direction of the dipole?
So I think like maybe, but we haven't. It's hard to disentangle yet. The reason I'm thinking yes is because in idealized simulation we don't have such effects, right? Because in idealized simulation you don't have this rotation or like tumbling of the halo. But we do it in cosmological simulation. Maybe that's why we are seeing different responses, exactly. So that's where all of these details start to matter. Like, for example, I know that what is the kinematic of the halo? The halo is very radially biased, have a lot of eccentric orbits instead of spherical orbits. The response is different, right? Maybe the type of dark matter too. So many effects start to take place. So now the name of the game is really to try to constrain those properties from the measurements that we have. Okay. Yeah, so basically the amplitude of these dipoles can give us information about the merger and the halo response of the galaxy, right? Now, let's also look at quadruples. That's the next order, right? And then quadruples, so have these shapes. Quadruples in general seems to be everywhere. Like all the halos have quadruples, and that makes sense because quadruples basically are showing you what is the principal axis of the halo, right? All of the halos are triaxial, are elongated, and a quadruple is a natural way to reproduce this kind of shape. So all of the halos have quadruples, even the ones that don't have LMC, like even this one, for example, is super triaxial, so you have a large quadruple that is, it has some variations as a function of time. However, we do see that at the pericenter passages, the ones with the LMC, you see like a peak in the dipole, in the quadruple, sorry. So it seems that the quadruple have a lot of information about the structure, the triaxiality, but also from the merger of the galaxy. Okay, I still have some time. So as expected, the amplitude of the quadruple is really correlated with these axis ratios, that these elongation values. So like you have a spherical halo, you don't have a quadruple, basically it's very low, but you have a highly triaxial halo, you have a large quadruple here. It's so confusing, but anyway. And then here you are seeing, for example, in the case of this one of these halos with the LMC, you see this quadruple set by filaments, but when the LMC comes, you see that the quadruple start like to tilt a little bit, right? Start like to move. So is the effect, the LMC also induces some quadruple because there is some wakes, there are some things, so the quadruple start to be more complicated. But yet it's important to understand because it's a large feature that we will see in the sky, right? We'll see these quadrupolar responses. So we really need to understand what's going on here. So this is something that Arpit Arora, who has a PhD at UPenn, looked into it, into quadruples, very detailed paper, but basically was saying, can we disentangle what is the effect from a satellite, from a filament in a cosmological simulation using this technique? So what you see here is, this is one of the fire halos in a cosmological simulation, and you see in the background is this filamentary structure, and then he overlaid some quadruples here. So in the one on the right hand, on your left, sorry, you will see a quadruple that is very aligned with the filament, right? That barely changes when the satellite comes. And the one here on the right, you see a satellite that is merging and then is inducing these quadruples that start to corrotate with the satellite, right? Which is consistent with something like the wake, for example, will induce a wake that is going to be rotating around the galaxy, corrotating with the satellite, and then you see that corrotation here. So what RP did is, because we have now this time series of quadruples changing as a function of time, you can correlate them temporally, like doing like some PCA analysis, some time series analysis to start to decompose the frequency of these quadruples. So I'm not going to go into the details, but it's just showing you the kind of things that we can do. And then basically it showed that the overall quadruple, the amplitude of the quadruple as a function of time decreases. This is because the filaments get thicker, so the amplitude of the quadruple is lower. But then you have these peaks which are coinciding with the pericentric passages from the satellite. So it's really, there are two quadruples being excited here. And then when RP decomposed them using this technique called multispectral singular spectral analysis, showed that the blue line is the one associated with the filament, and then the one in yellowish here, green, is the one associated with the LMC. So you can see that this one only peaks at the pericentric passages. So this is just to show you an idea of how quadruples will start to inform us about both the satellite but also the filamentary structure, but we need really to understand to decompose it. So it's more complicated than the dipoles. 5 minutes? Perfect. So right now in the Milky Way, we really don't know what is the filamentary structure in the Milky Way. There are predictions. This is a paper from yesterday, actually, in Nature. This is a okay, so these dot lines, these white dots here are satellites within 5 megaparsec or so around the Milky Way. And then this is a cosmological simulation that was tailored to reproduce the distribution of galaxies around the Milky Way. They run like 2,000 cosmological simulations, like in a Markov chain Monte Carlo fashion way. to try to constrain these properties. And the predictions are that we live in a cosmic sheet, right? It's not a filament, it's a cosmic sheet, it's a planar structure with these two underdensities. So these are the two projections. Here you see this kind of phase-on projections. You see the Milky Way, you see the M31 here in the inner parts, and then when you see it edge on, you see this a very thin sheet, right? These are predictions. This is what we get from trying to interpret the distribution of satellites in the near universe, but we haven't observed really this in stars yet.
So where is Virgo?
Virgo is here.
So that can be placed.
Yeah. Yes, that was one of the constraints. Yeah, good question. Yes, so we are starting to do these kind of things. So it'll be really fun if with all the surveys coming in the future, we can start measuring this cosmic sheet and the properties of this cosmic sheet. Right, that will be really, really exciting. So again, this is just to remind that in the near future, with these surveys, we're going to reach out maybe to these kind of regions here, and maybe you can start measuring this. What is the thickness of this sheet, and so on. Okay. So I just want to come back to here and say, like, okay, we have done some progress on developing more simulations, understanding what is the impact of these mergers. Dipoles are really important to understand the mergers. Quadruples for the filamentary structure. We now know how to compare between different simulations and the response using basis function expansions, but there is still more that we need to understand. And then just in the last 2 minutes, I want to mention what kind of methods now we can start to develop to put constraints on the properties of dark matter from the observations that we have. So this is something that Richard Brooks did when he was a pre-doc at the CCA. So Richard started to become, now everybody's thinking about simulation-based inference, doing, a lot of AI stuff, but really more based on statistics. And then you can ask, what are the parameters that we want to constrain? For example, what is the Milky Way mass and the shape, the LMC mass, what is the orbit of the LMC? Still, there is a lot of room. We have some constraints that we can do better. And what is the kinematics of the Milky Way, right? There is a dipole, there is not, and so on. So we can start asking these questions. And then, of course, then the data, using this data, like DESI, H3, and other surveys, we can start to constrain what are they, assuming some models, some simulations, right? So Richard developed 100,000 rigid simulations, so very simple. It's really hard to run 100,000 simulations realistically, embodied simulations. It will take a lot of energy, and it's not good for the environment. But we start simple, and the idea is to make this more and more efficient, right? So using this, oops, why did this happen? Okay, just basically start to constrain. Oh my God, can I move this really quick? Okay, let's see if it works. Oh no, okay, but you can put constraints, statistically constraints of what are the properties of the kinematics of the Milky Way halo in particular. So this is a very nice method to start to understand how these simulations and the data can start to help us understand more the parameter space that so far is unknown. So people have developed more simulations, and I'm going to show here what Sheng has done in 2 papers, actually, sampling like 20, almost like 3,000 simulations of the Milky Way and the LMC with different orbits, different mergers, mass ratio of the mergers, different shape of the Milky Way, different concentrations for the Milky Way. But all of these orbits reproduce the present-day position of the LMC. So you see that still there is a lot of parameter space here, right? How to constrain what is the orbit exactly of the LMC. And then the idea is with these methods to start to constrain, again, with the data, start to constraining properties of this parameter space. Something else that we are doing that I'm going to talk more at the lunch, that I didn't have the time to talk right now, is to compile all of these methods, all of these simulations using basis function expansions. I can create a library of time-dependent potentials that will allow us to integrate orbits of all the halo stars in the outer parts of the galaxy. As I show you, since the LMC is perturbed with the Milky Way, it's really hard to recover the orbits if you don't have this time-dependent potential. So I'm compiling this library that is going to go live on the site server at Johns Hopkins. So anybody can use it to integrate orbits. So my conclusions of this colloquium are like the exquisite data of the Milky Way, the stars in the Milky Way, are allowing us to prove fundamental properties of the cold dark matter models and galaxy formation, right? How many satellites there are, what is the shape of the halo. And over the past decade, really, we have now have a more complete picture of what has been the accretion of history of the galaxy. You have the GSE merger, you have Sagittarius, and the LMC has been detected throughout the galaxy. And we also measure the effects across the galaxy, in the inner halo, in the disk, in the outer halo. So that's very exciting. And really the LMC in particular, the ongoing merger with the LMC will allow us to prove even more because we have a wake, a reflex motion that will tell us more about the underlying dark matter halo of the Milky Way, the response of the Milky Way to this merger. And then future data sets are really going to help us to improve what is the halo response to the LMC, but also to the large-scale structure and the filaments in the outer parts of the galaxy. So thank you very much for your attention.
Any questions?
Great talk. So there was recently a paper that suggests there's a GSE size merger that happened like before GSE, right? And would you predict there's any you'd be able to observe any relics of this, or did GSE come in, phase mix everything, and then dominate the halo?
Is this the one with the globular clusters, I guess?
Yeah.
So the thing, like, the earlier the merger, so it had been more time for the halo to relax. Still for the GSE, we see some remnants. But overall, I do think that once you have a new merger coming up, that will erase the signatures of the previous merger. But the halo response will be different because that is different if you start with a halo that is spherical, that is like already being perturbed. So the halo response will be slightly different. So there might be some signatures, but although we only have globular clusters, it's going to be hard to. But it's exciting for understanding how the galaxy has been assembled over time. I think that's very, very useful because then we can put constraint. What was the mass ratio of that merger? Is that consistent with CDM or like not? So
Absolutely. Yeah. Thank you.
That's great.
Other questions?
It's a very nice talk. So you mentioned that, I think you implied that better simulations are needed to study self-interaction.
Yeah.
What about the data? Do you think the data needs to be much better?
Always.
Always, yeah.
Always, yes. But
question.
I guess from the data side, we do need to have, the better proper motion, the better radar velocities is going to be easier to constrain, especially in the outer halo, right? So you have will be more constraining of the models. For sure.
Yeah, I have a related question. I was curious how well in real data the different multipoles can actually be calculated. Like how precisely do we know that?
We haven't done actually that yet. We have just recently done it in simulation, but I think the next step will be, because so far we have these maps of the velocities in the outer regions and the densities, but we haven't quantified that in terms of the multiples, right? And I think that would be really useful to have like a metric that we can say, okay, this density map is telling us this amplitude of the dipole, this amplitude of the quadrupole, and then we can relate how much that corresponds to the dark matter. So that's where we are right now. But I think that would be the features. And especially with Gaia DR4, we're going to have many, many more stars. It will be really exciting to do at the end of the year, for sure.
On that note, have you done any forward modeling of stellar basis functions, or is this all purely dark matter so far?
There are for the disk. So the disk can be very well described, very well, but the Milky Way disk can be very well described by basis function expansions. Mm-hmm. Things like the LMC, for example, Himansh Rathore, a grad student at Arizona, is doing it, and then he can recover the LMC. But something like the SMC, for example, that is very disrupted, is really hard to do with basis function expansions at the moment.
All right.
But yeah, something like the stellar halo is really complicated too because it's very lumpy. That's hard. That you need, but that for the stellar halo, you can use the basis function for the dark matter halo and then throw in a simulation 10 to the 8 particles. That's super easy nowadays, and then you can have a fully stellar halo, very well resolved with M-body. So those kind of things we can start doing right now. For example, with the SMC Atlas, we have these 2,000 simulations, then we can put the stellar halos in all of them, and then start comparing with the data.
Any final questions?
The dynamic halo is clearly correct, but I'm just curious, at what timescale does it no longer matter, right? So for very short integrations, it's effectively static, is that right?
Can you repeat the question?
What's the timescale for this dynamic halo?
When
does it start mattering for the orbits you're calculating?
So it depends for the LMC, it's the last 2 gigayears, right? That's where you start to see the differences. But for example, Scott has shown that for hypervelocity stars, it's very recent, right? Because the hypervelocity stars were ejected like very recent. So maybe for that regime, it doesn't matter all the perturbations. But for something, for example, for the Sagittarius stream, which is wrapping the galaxy multiple times, for that, you cannot do it without the LMC. So,
Of course.
so it depends on the time scales of the stars that you're thinking about. Yeah. Thanks.
All right, we could have time for one more question if anyone has any remaining burning questions to ask. Or we're perfectly on time then. Everyone, let's thank Nico again.